So today we are going to discuss about the Gibbs adsorption isotherm in the third year BSc syllabus. Various adsorption isotherm has been studied by us. In that, Langmuir's adsorption isotherm, Freundlich adsorption isotherm, and BET adsorption isotherm. But in this lecture, I would like to discuss about Gibbs adsorption isotherm. So this adsorption isotherm was given by the Gibbs, hence it is called as Gibbs adsorption isotherm. So we know that the free energy of a system of two components, suppose if we have taken the two components here, solute and solvent here, suppose this is solvent water, and we are adding the solute here. Suppose that solute, it is sodium chloride, it is a solute, so therefore it is a solution of sodium chloride in water. So the free energy of a system of two components, which are the two components? Water is a one component and sodium chloride, it is a another component, where sodium chloride, it is a solute and water is the solvent. So the derivation of the free energy of a system of two component, it is given by, so G, it is equal to gamma into S, where this gamma, it is called as a surface tension, because due to the addition of the solute in the solvent, there is a surface tension, either it will be increases or decreases. So gamma, it is the surface tension, and S, it is the surface area. S, it is called as a surface area here. Okay. Now plus N1 mu1 plus N2 mu2. Actually, we know the free energy, it is equal to chemical potential for one component system, where number of moles, it is equal to 1. But now in this case, we consider the two components, and number of moles of the two components are N1 and N2. Therefore, the free energy, it is equal to gamma into S, because of due to the surface tension, here there is a free energy will be changes, and on the same time we have to consider the surface area also. So gamma into S plus N1 mu1 plus N2 mu2, this is our equation 1. So free energy, it is related to gamma into S plus N1 mu1 plus N2 mu2. What is N1 and N2? N1 and N2 are the number of moles of the solvent and solute respectively, where N2, it is the number of mole of sodium chloride, and N1, it is the number of mole of the water, because water is a solvent here. What is mu1 and mu2? Mu1 and mu2, it is a chemical potential of a solvent and solute. Now let us going to differentiate this equation 1. So do the differentiation of this equation. So differentiation of G, it is dG. Okay, so dG equal to, so it is gamma into ds plus S into d gamma. The differentiation of this gamma into ds plus S into d gamma. Similarly here, differentiation of this term N1 into d mu1 plus mu1 into dN1. Similarly here, N2 into d mu2 plus mu2 into dN2. So we know how to differentiate this equation 1. So the differentiation of this equation 1, now it is dG equal to gamma into ds plus S into d gamma plus N1 into d mu1 plus mu1 into dN1 plus N2 into d mu2 and mu2 into dN2. This is our equation 2. Now let us simplify this equation 2. But before to simplify the equation 2, we know that the free energy G, It depends upon temperature, pressure, and number of moles of the constituent. In this system, as we have taken the two constituents, water and sodium chloride. Water plus sodium chloride. Okay, sodium chloride, it is a solute, and water is a solvent. So for this system, the free energy, it depends upon temperature, because free energy will be changes when temperature will be changes. The free energy, it is a function of pressure. As the pressure will be changes, free energy will be changes. The free energy, it will be the function of number of moles of the constituent. As we have changed the number of moles of the constituent, the free energy is also changes. So mathematically, we can write free energy G, it is equal to function of temperature, pressure, and number of moles of the constituents, where N1, it is the number of moles of the water, and N2 is the number of moles of the solute, that is sodium chloride. Now let us going to differentiate this equation. Okay, so differentiation of G, it is equal to dG. So differentiation of G with respect to temperature at constant pressure and composition. Okay, so we can write mathematically this change in the free energy with respect to temperature, that is delta G upon delta T, keeping pressure and this constant N1, N2, that is composition is constant here, into dt, change in the temperature, plus change in the free energy with respect to pressure, now keeping temperature and number of moles constant here. Okay, so change in the free energy with respect to pressure at constant temperature and composition into dP. Similarly, now change in the free energy with respect to number of moles of the first constituent, that is suppose N1, it is the number of mole of the solvent. So if we change the number of mole of the solvent, then free energy will be changes. So it can be written as change in the free energy with number of moles of the solvent, that is delta G upon delta N1 at constant pressure, temperature, and this N2 is also remains constant here, that is the number of moles of the sodium chloride remains constant into dN1. And last one, it is the change in the free energy with respect to number of mole of the second constituent, that is a solute, at constant pressure, temperature, and number of moles of the solvent remains constant here into dN2. So this is the very important step of the derivation, the differentiation of this change in the free energy, that is dG. So change in the free energy with respect to temperature. So this is the term with respect to temperature. Change in the free energy with respect to pressure. So this is the term which represents change in the free energy with respect to pressure. Then change in the free energy with respect to number of moles of the first constituent. So this is the term represents. By keeping other constant, at a one time we can only change one variable here, either temperature, pressure, or number of moles of the constituent. So we get here the equation 3. But actually we know that the change in the free energy with respect to number of moles, it is nothing but partial molal free energy. Okay, it is also known as partial molal free energy. Partial molal free energy, and this partial molal free energy, it is also called as chemical potential. So we can write here partial molal free energy, that is delta G upon delta N1, it is equal to mu1. Similarly, delta G upon delta N2, it is equal to mu2. So we can substitute here, this is mu1 and this is mu2. This is according to the definition of the partial molal free energy. What is partial molal free energy? It is nothing but the change in the free energy with respect to number of moles of the constituent at constant pressure, temperature, and other moles of the constituents are constant there. And that partial molal free energy, it is also called as a chemical potential. This is also called as a chemical potential here, and it is denoted by mu1 for this first. So therefore we can write this is mu1. Okay, it is mu1 here, it is mu2 here. Okay, so now at constant temperature and pressure, suppose we keep the temperature constant, we keep the pressure constant. Therefore, we can write here dt equal to 0 at constant temperature, no change in the temperature. Similarly, dp equal to 0. So this equation 3 can be written as, so the first two terms are 0 here, because dt equal to 0, dt, so 0 multiplied by this term, it is 0. So 0 multiplied by this term, it is 0. So therefore, we can write now the equation 3 in this way, dg equal to mu1 dn1 plus mu2 dn2. This is our equation 4. Okay, change in the free energy dg, it is equal to mu1 dn1 plus mu2 dn2. So we are getting this equation 4 now here. Now, to get the total free energy change, the increase in the free energy due to increase in the surface area should be included. We are talking about the solute and solvent. So when we are adding the solute into the solvent, you can see here, when we are adding the solute into the solvent, the surface area will be changes here. Okay, you can see the surface area will be changes because we are adding the solute here and some solute molecules are here, and due to that vapor pressure is also changes here on the surface. On the surface, the vapor pressure is also changes due to the addition of the solute, and on the same time the surface area will be changes as well as free energy will be changes. So what is that total free energy? So to get the total free energy change, the increase in the free energy due to increase in the surface area, it should be included. Okay, it should be included there. So try to understand. So if gamma is the surface tension and ds is the increase in the surface area, ds is the increase in the surface area, you can see that here, ds is the increase in the surface area. Okay, initial surface area and final surface area, means without addition of the sodium chloride, the initial surface area will be less here, and due to the addition of the sodium chloride, the surface area has to be increased here. So ds is the increase in the surface area, and gamma it is called as the surface tension. So this has to be included here in the total free energy. Okay, so therefore the equation will be changes now. So to get the total free energy change, the increase in the free energy due to the increase in the surface area should be included. Okay, so gamma is the surface tension and ds is the increase in the surface area. Then the increase in the free energy due to the increase in the surface area, it is equal to gamma into ds. Okay, increase in the free energy due to the increase in the surface area, it is equal to gamma into ds. So we should have to add this term now into equation this 4. Okay, into the equation 4 we have to add gamma into ds here, because the total free energy change now it will be changes in the case of the solution of the solute and solvent. As we are adding the solute into the solvent, the surface area has to be increased. So surface tension multiplied by the increase in the surface area, it is called as increase in the free energy due to the increase in the surface area. So it is gamma into ds. So in this equation we have to add gamma into ds. So equation 4 can be changes too. So let us see now the equation 4. Change total free energy change dg, it is equal to gamma into ds plus mu1 into dn1 and plus mu2 into dn2. This is equation 5. Okay, so we are getting here the equation 5. Now subtracting equation 5 from equation 2. So I would like to write here the equation 2 here once again. So equation 2 should be equal to C. You can see here, this is the equation 2, gamma into ds plus s into d gamma. So I would like to write this equation here to simplify now. So dg, it is equal to equation 2 dg, it is equal to, previously we have written gamma into ds plus s into d gamma, okay, plus mu1 n1 into d mu1 plus mu1 into d n1, okay, plus mu2 n2 into d mu2, n2 into d mu2 plus mu2 into d n2. This is our equation 2. Now subtracting this equation 5 from equation 2. Okay, so dg equal to this gamma into ds. So you can see this gamma into ds. This is there. Then mu1 into dn1. So mu1 into dn1. This is there, and mu2 into dn2. So we can write dg here in place of this equation. So by subtracting now this equation 2 from equation 5, we will get here. So what we get? So I would like to write simplify this equation 2 here first. So we can write dg equal to. So dg equal to dg. Okay. This term you can see, this is 1, this is 2, this is 3. Okay. So in place of these 3 terms, because equation 5 becomes equal to dg equal to. So I would like to write remaining terms now. It is mu1 dn1, mu1 dn1. So we can write n1 d mu1, n1 d mu1 plus n2 d mu2, and remaining term is this s into d gamma, s into d gamma. So dg get cancelled. Okay. So now n1 d mu1 plus n2 d mu2 plus s into d gamma, it is equal to 0. You can see here, s into d gamma plus n1 d mu1 plus n2 d mu2, it is equal to 0. This is our equation 6. Okay. So we derive here the equation 6, s into d gamma plus n1 into d mu1 plus n2 into d mu2, it is equal to 0 here, equation 6. Consider there are only 2 phases, namely surface phase and bulk phase. This is called as a bulk phase. You can see this diagram. This is called as a bulk phase, and this is called as a surface phase. There are only 2 phases we have to consider. Okay, so it is known that only surface phase and bulk phase are there. Now it is known that only surface phase is attracted by surface forces. This surface phase is attracted by surface forces, and bulk phase remains unaffected. So this is the bulk phase, it is remains unaffected, it is not going to be attracted. So surface phase, it is only attracted by the surface forces. Okay, so let us consider now n1 and n2 be the number of moles of the solvent and solute in the surface phase. This is the surface phase here. So see here, this is the surface phase. Okay, so here n1 and n2 be the number of moles of the solvent and solute in surface phase, and n10 and n20 are the number of moles of the solvent and solute in the bulk phase. This is bulk phase here. So n10 and n20 is the number of moles of the solvent and solute in the bulk phase. So try to understand this. n1 and n2 are the number of moles of the solvent and solute in the bulk phase. This is surface phase, and this is the bulk phase here. So let us assume this. Now according to this, what is the change is there? So we can change now the equation, this Gibbs-Duhem equation we can change now. We know Gibbs-Duhem equation, that is n1 d mu1 plus n2 d mu2, it is equal to 0. This is Gibbs-Duhem equation. So in the bulk phase, we can write this equation in this way. Bulk phase, n1 0 d mu1 plus n2 0 d mu2, it is equal to 0. This is for the bulk phase, because in the bulk phase the solute and solvents are there in the pure state. Now multiplying equation 7, this is equation 7, can be obtained from this Gibbs-Duhem equation. Gibbs-Duhem equation, this equation it is known to us. Gibbs-Duhem equation. Now multiply equation 7 by this term, N1 upon N10. What is N1 here? N1 is the number of moles of the solvent at the surface phase, and N10 it is the number of moles of the solvent at the bulk phase. Okay, so we can do this now. Multiply this N1 upon N10 to this. So if we multiply this N1 upon N10, so in this case N10 get cancelled. So N1 d mu1, and it is multiplied by this N1 upon N10. So it is N1 N20 divided by N10 into d mu2 equal to 0. This is our equation 8. Okay, so we modify this Gibbs-Duhem equation in the bulk phase. So it can be written in this way, and it should be multiplied by N1 upon N10. Multiply this equation. So N10 get cancelled. So we can write this equation in this way, equation number 8. Now subtracting equation 8 from 6. Let us see the equation 6 here once again. So this is our equation 6 here. S into d gamma plus N1 d mu1 plus N2 d mu2 equal to 0. So I would like to write this equation 6 here once again. So S into d gamma, okay, plus N1 into d mu1 plus N2 into d mu2, it is equal to 0. This is our equation 6. So subtracting equation 8, this is our equation 8 from equation 6. Now we will get here subtracting this equation. So what will be get cancelled? So this N1 d mu1 and N1 d mu1 get cancelled here. So what are the remaining terms? S into d gamma. Okay, so S into d gamma. Okay, then what is remaining here? N2 minus. Okay. Let us take the common here. Now d mu2 is here, this term containing d mu2. Similarly N2 into d mu2. So what is that remaining term? N2 into d mu2 minus, okay, subtracting equation 8. So this is another term, it is N1 upon N2, N1 into N20 divided by N10. So let us do the subtraction of this equation. Then we can get here N2 minus N1 into N20 divided by N10 into d mu2. So out of the bracket we have to take here d mu2 equal to, now it becomes equal to 0. So this is the result of subtracting equation 8 from equation 6. This is our equation 6. By taking d mu2 as a common, we are getting this equation S into d gamma. Now let us rearrange this equation 9. Okay, so taking this minus S into d gamma, okay, it is equal to N2 minus remaining term will be N1 into N20 divided by N10 into d mu2. This is our equation 10. Now we can write the equation 10 now in this way, taking this d mu2 on this side. So d gamma upon d mu2, and S will be on this side. Okay, this is having the negative sign here. So it is N2 minus N1 into N20 divided by N10 divided by S here. Okay, so d gamma upon d mu2, it is equal to just modification of this term into this equation. Okay, so d gamma, taking this d mu2 here, d gamma upon d mu2, it is equal to, so we are getting this equation now. This is our equation 11. This is our equation 11, d gamma upon d mu2, it is having the minus sign here. Okay, because we write this equation 1, so this will be goes to this side, so it is having the minus sign. So minus d gamma upon d mu2, it is equal to this. This is our equation 11. Now equation 11 can be modified as the quantity, this quantity N2 minus N1 into N20 divided by N10 divided by S. In that equation 11, you can see this is the equation 11 here, minus d gamma upon d mu2. So once again, I would like to write that equation here, minus d gamma upon d mu2. Okay, it is equal to N2 minus N1 N20 divided by N10, and it is divided by S. Okay, this is our equation 11. Now this quantity, it is known as excess concentration of solute. What is N2 here? N2, it is the number of moles of the solute. Okay, so N2 minus this, So it is the excess concentration of the solute per unit surface area. Okay, so you can see this is the surface of the liquid, and in the surface of the liquid there are solute molecules. N2 number of the solute molecules are there, because on the surface there are excess number of the solute molecules are present as compared to the solution, as compared to the bulk phase. So N2 minus N1 into N20 divided by N10 divided by S, it is called as, this quantity it is known as excess concentration of the solute per unit surface area divided by S. So it is per unit surface area, and it is denoted by the symbol tau. Okay, this is a symbol tau, can be represented in this way. So we can write here tau, it is equal to, okay, minus d gamma upon d mu. Okay, this is represented by tau here, so minus d gamma upon d mu. This is our equation 12. D gamma, it is change in the surface tension with respect to change in the chemical potential, d mu. But according to the definition of the chemical potential, mu it is equal to mu 0 plus RT ln A2, where A2 is the activity of the solute. Okay, actually the equation will be like this: mu equal to mu 0 standard chemical potential plus RT ln A. This is the equation here. So in case of this, because we are adding the solute here, excess quantity of the solute is here, so let us convert this A2. So mu equal to mu 0 plus RT ln A2. This is our equation 30 according to the definition of the chemical potential. According to this equation of the chemical potential, we can write this, where A2 is the activity of the solute. Okay, now at constant temperature, differentiating equation 13. Temperature is constant, and let us going to be differentiate this equation, or we can write here mu 2. Okay, mu 2 it is the chemical potential of the solute, and mu 1 it is the chemical potential of the solvent. So mu 2 it is equal to mu 0 standard chemical potential plus RT ln A2, where A2 is the activity of the solute. Now at constant temperature, differentiating this equation, let us do the differentiation. So differentiation of mu 2, it is d mu 2, right? Now mu 0 it is a constant term, so it cannot be differentiated. Now differentiation of this RT ln A2, it is RT derivative of ln A2. Okay, RT at constant temperature, so RT remains same, it cannot be changed. But what is the differentiation of this ln A2? It is derivative of ln A2. So it is equal to RT. What is derivative of ln A2? Derivative of ln A2, it is equal to dA2 divided by A2. Just like derivative of ln x. What is the derivative of ln x? It is 1 upon x into dx. Okay, so derivative of ln A2, it is 1 upon A2 into dA2. Okay, so dA2 upon A2. So we can write here, you can see RT into dA2 upon A2, d mu 2 equal to. So substitute this d mu 2 here into this equation 12. Okay, so we can write now this equation d gamma upon RT into dA2 into A2. Okay, because A2 goes to the numerator. So tau it is equal to, so the equation can be written as minus d gamma divided by RT into dA2. Okay, RT into dA2 into A2 here. So this is the equation, I think, the Gibbs adsorption isotherm. Okay, this equation, I think it is equation number 13. You can see that same equation can be written in this way. Minus sign should be taken on this side here. Okay, minus A2 upon RT. This equation can be simplified here. Minus A2 upon RT into d gamma upon dA2. You can see minus A2 upon RT, d gamma upon dA2. So this is the equation called as a Gibbs adsorption isotherm. For a very dilute solution, activity becomes equal to concentration. If the solution is very, very dilute, then activity it becomes equal to the concentration. Okay, actually activity it is equal to molality into gamma. For a dilute solution, gamma it is equal to 1. So activity it is equal to concentration. Okay. So you can simplify this equation now. This is C. So we can write the equation gamma equal to minus C upon RT into d gamma upon dc. So this is the Gibbs adsorption isotherm. What is d gamma? Change in the surface area, surface tension, and dc it is the change in the concentration. So at the surface of the liquid, there is a change in the surface tension as well as change in the concentration. So this is the equation called as a Gibbs adsorption isotherm, that is tau it is equal to minus C upon RT d gamma upon dc. So in this way, we derive here the Gibbs adsorption isotherm. So try to understand this. This is the Gibbs adsorption isotherm, and in this way, we derive the Gibbs